Hello, we're going to talk about the standard normal distribution and its importance. Now, we've seen a few normal distributions in the past videos. So these normal curves were graphed on the same axis, and so you have a normal distribution with mean, mu, and a standard deviation of 1, and then they change with mu. We're going to the right here the graph with mu equals -2, -1, 0, 1, and 2. And you can see what happens over here. At -2, this is the graph of mean 2, and here's -1, and then 0, then 1, and then 2, and so on. So what happens to the graph as our mean changes? Well, it just kind of shifts over left and right depending on what your mean is, and so on. So that's what the changing the mean shifts it left and right. And so that brings us to parameter m determines the position of a normal curve with relation to the y-axis, right? So that's what tells us how far it's going to shift in either direction. And then we've seen in a previous video where I plotted up a bunch of distributions and just changed its standard deviation. You can see what happens. 0.25, that standard 0.25 makes it kind of crunches it together and pushes it up. Whereas it gets the more standard deviation, the more spread out it gets. You can see here's 9, and it gets really spread out distribution. Where if you have 0.25, it's real narrow, and that's what it does. So the mean shifts left and right, shifts the graph, but the standard deviation will either crunch it or flatten it out, depending on those numbers. So a big standard deviation will make it real flat, whereas a very small, everything's crunched in together right here. So next, let's go ahead and look up here, and some notation that we're going to have. It says all normal curves can be related to a single reference distribution called the standard normal distribution. I've already kind of mentioned that before, but now we're going to talk about it more formally. The standard normal deviation, which has a mean of 0 and a standard deviation of 1. And then the standard normal variable is denoted by z. So when we use z, we're talking about the specific normal distribution that has mean 0 and standard deviation 1. So it's the mean's right at the it's right at the x-axis. That's right on the y-axis, and it's normal distribution. I mean, it's standard deviation 1 is just 1 from that mean. And then the PDF of z is always denoted by this little v right here, and the CDF is the capital letter V right here. So, and this is one we're going to use most often than this one. So, first example they give us to start with, right, is this guy. It says consider the standard normal distribution z to be 0, 1. Find the value of this guy right here. So what does that mean? A asks us for a CDF of 1, right? Well, that is the area under the curve, right? The area under the curve of a standard normal deviation. Well, if I drew up the graph right here, it's the standard normal that looks something like this, right? Good. And where is this area under the curve, right? This area under the curve is 1, right? So, or better yet, it goes to 1, right? My bad, it's not the area. It goes to 1 over here. So I can go ahead and use my calculator to calculate that out real quick. So I'll go on here, and I go menu. This is, I'll go to statistics, distributions 5, and a CDF normal distribution, and it's going from negative infinity all the way to 1, and then that is this guy right here is going to come out to be 0.84134, and so on, and that's what that's equal to. Now B, it asks us for its inverse, right? So for B, it asks for the CDF inverse of 0.8, which, if you notice, this accounts for this area right here. This area right here is 0.8413, right? And so on. So it should be pretty close to what we have up here, right? Which is right up there. So let's do the inverse menu. 6, distributions 5, and now we're going to do the inverse normal and our area is just 0.8, and it is a standard normal, so I'll keep it like this. And then I'll go like this, and you can see it's really, really close to it. So that is equal to 0.8416, and so on, right? So that's what I got. So you can see they're pretty close. Next concept I'm going to talk about is, and it should relate back to what we were talking about. We saw that when we have a standard normal variable, if you solve a problem for where you do not know where the mean or variance of normal variable, you have to use the standard normal variable. To standardize a normal variable, so you have some x follows a normal distribution with some mean and some variance into a standardized normal. To this guy, you use the transformation here. And you could make sense, right? So if you could kind of make sense of what's going on here, right? This is good. Or if I rate the z equal to 1 over standard deviation x minus the mu, right? This is going to shift the mean over whichever way it is, depending on whatever your mean is, right? It gets it right there. And this guy right here is going to, well, if you think about it, inside the function, we plug it inside a function, this 1 over theta, what would it do? It'd be 1 over that. So it's scale factor, it's x scale factor. If it's 1 over x, it's 1 over that, so that's going to make that. So the bigger that number is, the more spread it out it's going to be. And you can see how that works. So if you think back to our translations to other units. So, so we can use this to solve certain problems. And we call this sometimes we'll call this the z-score, or you're standardizing something, you're standardizing it to be able to standardize it to make it a standard deviation, right? So that's a standard normal distribution, right? So they call this standardizing it. So the problem that they looked at us over here, and it says, consider x is a normal distribution with mean 2 and variance 3 squared, or standard deviation 3. Calculate first p is less than or equal to 1. So p is, for x is less than or equal to 1, right? So for this guy right here, I'll go ahead and, here, I'll just write it right here. Put it right here. So the first one right here is probability that x is less than or equal to 1. So I'll use the calculator, and I'll go menu 6, 5, CDF probability normal distribution. Since it's less than 1, I'll use the small one, and it's going to go up to 1. So, but this time for this one, for x, it's actually got, it's not a standard normal, it's got a 2 as our mean, and then its standard deviation is 3. And then I get this number, and I get is equal to 0.3694, right? But it also wants to find out if it's a normal distribution here, so I can look at it this way. If z is less than or equal to negative 1/3, right? But what is z equal? If z is equal to whatever my random variable x minus its mu, right? So I can say probability of x minus, what's our mean in this situation? It's 2. And what's our standard deviation? Is 3, less than or equal to negative 1/3. And then I can solve this guy right here to see what this is equal to, right? So if I multiply both sides, what's inside of here by 3, I'm going to get the probability of x minus 2 less than or equal to negative 1, because 3 times this gives me negative 1. And then I add 2, and I get the probability that x is less than or equal to, add to 1, and you can see it comes out to the exact same thing that I have up here. Now that I standardized it, I can say that, well, this is equal to 0.3694, right? And basically the same thing happens with the other guy right here. So it says to calculate this, so I'll go to the calculator. And I'll use the standard normal variation, the normal CDF, and then I'm going from negative 1 to 2. So I can just negative 1 to 2, and it's still a mean of 2 and a standard deviation of 3, and I get 0.34. So for this guy, I get probability that negative 1 is less than or equal to some random variable x is less than or equal to 2. That comes out to 0.3413. But then they want us to check for the standard normal, right, which is z. Well, if you look at this guy right here, I can say the probability that negative 1 is less than or equal to z is less than or equal to 0, but I know that the standard normal is equal to the random variable x minus its mu over its distribution, so over its standard deviation, and then I can say negative 1 less than or equal to z is x minus, in this situation it's 2 again, all over 3, less than or equal to 0, and then we can see that, well, if I multiply by 3, I'm going to get probability of negative 3 less than or equal to x minus 2 less than or equal to, well, 3 times 0 is still just 0, right? And then I'll just go this way, add 2 to this way, I'm going to get is probability to negative 1 less than or equal to x less than or equal to 2, right? And you can see this comes out to the same probability that we had to begin with, which is, oh, this was between 2, right? And but I did write it right in here, between negative 1 and 2. Negative 1 and 2, I wrote it wrong right here, which is the same answer, right? So this guy here ends up being the exact same thing that we have here, so this guy right here is equal to 0.3413, and there you go. So we can use the standard normal distribution, its parameters to, sometimes we say it to normalize. We normalize this distribution. It helps us out with certain problems. And there you go. Thanks.